NFPA 70, commonly known as the National Electrical Code, or NEC, Article 250.114 dictates that metal flooring must be grounded in accordance with 250.118. Article 250.118 further elaborates on this, specifying that the metal frame of a surface floor raceway shall be grounded by an equipment grounding conductor, as outlined in 250.118 or B. The alternative method involves grounding the metal frame of a surface floor raceway to a grounding bus, following the guidelines in 250.118 Bone or B2. Notably, the grounding bus itself must be bonded to the grounding electrode system, adhering to the stipulations of 250.40. Now let's break down what this means in practical terms, especially concerning raised flooring pedestals. The code considers pedestals of raised flooring as metal flooring. Therefore, they fall under the purview of NEC 250.114 and 250.118. This means grounding is mandatory. This requirement exists regardless of the room's specific purpose. Whether it's an information technology telecommunications room, commonly abbreviated as ITT, or a standard office space, the grounding imperative remained. Grounding, in essence, provides a safe path for electrical fault currents. It minimizes the risk of electrical shock and fire hazards. When a fault occurs, the grounding system facilitates the quick tripping of a circuit breaker or fuse. This action effectively cuts off power to the faulty circuit. The objective is to prevent dangerous voltage from persisting on exposed metal parts. Think of the metal frame of a device. Picture the metal flooring in a building. This reduces the potential for electrical shock to individuals who might come into contact with these surfaces. Now, let's explore the intricacies of NEC Article 250.118 in greater detail. Firstly, the equipment grounding conductor method 250.118 necessitates the use of a conductor specifically designated for grounding purposes. This conductor can be a wire or a metallic raceway. It connects the metal frame of the surface floor raceway to the building's grounding electrode system. The grounding electrode system itself is a network of interconnected grounding electrodes. These electrodes are typically ground rods, metal underground water pipes, or building steel structures that are in direct contact with the earth. The size of the equipment grounding conductor is critical. It's determined based on the size of the overcurrent protective device protecting the circuit. This information can be found in NEC Table 250.122. For example, if the overcurrent protective device is rated at 20 amps, the minimum size of the copper equipment grounding conductor would typically be 12 American wire gauge, or oak. Secondly, the grounding bus method 250.118b introduces the concept of a grounding bus. This grounding bus serves as a central point for connecting multiple equipment grounding conductors. It's essentially a common grounding point for various metal components. The grounding bus is then connected to the building's grounding electrode system, complying with the requirements outlined in 250.40. This ensures that all grounded components are effectively connected to the earth. Proper bonding is crucial for the grounding bus. Bonding refers to the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to safely conduct any fault current likely to be imposed on it. The bonding connections must be mechanically strong and electrically conductive. They should be made using methods approved for the purpose. Examples include exothermic welding, listed pressure connectors, and bolted connections. Now let's delve into the implications of 250.40, which mandates that the grounding bus be bonded to the grounding electrode system. This bonding connection must be made in accordance with the requirements of 250.50. 250.50 specifies the different types of grounding electrodes that can be used. This article also explains how they should be connected together to form a comprehensive grounding electrode system. Common grounding electrodes include ground rods, which are typically copper or copper-clad steel rods driven into the earth. Metal underground water pipes, provided they meet certain requirements, can also serve as grounding electrodes. The building's steel structure, if it's effectively grounded, can also be utilized. The size of the bonding jumper connecting the grounding bus to the grounding electrode system is determined based on the size of the service entrance conductor. NEC Table 250.66 provides guidance on selecting the appropriate size of the bonding jumper. The objective is to ensure that the bonding jumper is capable of safely carrying any fault current that might occur. It's important to note that the NEC provides specific requirements for the installation of grounding electrodes. For example, ground rods must be driven into the earth to a minimum depth. The connection between the grounding conductor and the ground rod must be made using approved methods. These methods include exothermic welding or listed grounding clamps. When using a metal underground water pipe as a grounding electrode, the pipe must be in direct contact with the earth for a minimum length. The connection to the water pipe must be made on the street side of the water meter. This helps prevent the possibility of the water meter becoming a point of high resistance in the grounding path. In summary, grounding the pedestals of raised flooring is not just a recommendation. It's a requirement rooted in the NEC. This requirement ensures electrical safety and minimizes the risk of electrical hazards. Regardless of the room's purpose, the grounding of metal flooring, including raised flooring pedestals, must comply with NEC 250.114 and 250.118. Following these guidelines contributes to a safer electrical environment. Now let's dive into some of the common misconceptions surrounding grounding. One common misconception is that grounding is only necessary in ITT rooms or areas with sensitive electronic equipment. While it's true that grounding is particularly important in these environments to protect against electrostatic discharge and electrical noise, the NEC mandates grounding for all metal flooring, regardless of the room's function. Another misconception is that simply connecting the metal flooring to the building's steel structure is sufficient grounding. While the building's steel structure can serve as a grounding electrode, it must be properly connected to the grounding electrode system. The connection must be made in accordance with the requirements of 250.50. Furthermore, the metal flooring must be bonded to the building's steel structure using approved methods. A third misconception is that grounding is not necessary if the electrical equipment in the room is double insulated. Double insulated equipment is designed to prevent electrical shock even if a fault occurs. However, the NEC still requires grounding of metal flooring, regardless of whether the equipment is double insulated or not. This requirement is intended to protect against other potential electrical hazards. These hazards include static electricity and stray currents. It's also crucial to understand the role of the authority having jurisdiction, or OJ. The AHJ is the organization, office, or individual responsible for enforcing the requirements of a code or standard. In the context of electrical installations, the AHJ is typically a local building inspector or electrical inspector. The AHJ has the authority to interpret the NEC and to approve or disapprove electrical installations. Therefore, it's important to consult with the AHJ to ensure that the grounding of raised flooring pedestals complies with all applicable requirements. The AHJ may have specific requirements or interpretations that go beyond the basic requirements of the NEC. Now let's talk about the practical aspects of grounding raised flooring pedestals. The most common method is to connect each pedestal to the building's grounding electrode system using an equipment grounding conductor. The size of the equipment grounding conductor is determined based on the size of the circuit supplying power to the room. This information can be found in NEC Table 250.122. The equipment grounding conductor can be connected to the pedestal using a variety of methods. These methods include listed grounding clamps, exothermic welding, or bolted connections. It's important to ensure that the connection is mechanically strong and electrically conductive. In some cases, it may be necessary to install a supplemental grounding electrode system specifically for the raised flooring. This is particularly common in large ITT rooms or data centers. The supplemental grounding electrode system typically consists of a network of ground rods interconnected with a copper conductor. The ground rods are driven into the earth around the perimeter of the room. The copper conductor is then connected to each of the raised flooring pedestals. This creates a low-impedance grounding path that helps to minimize electrical noise and protect against electrostatic discharge. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections should be inspected periodically to ensure that they are tight and free from corrosion. The resistance of the grounding system should also be measured to verify that it is within acceptable limits. If the resistance is too high, it may be necessary to add additional grounding electrodes or to improve the existing grounding connections. Grounding is a critical aspect of electrical safety. When properly implemented, it helps to protect people and equipment from electrical hazards. By understanding the requirements of the NEC and following best practices for grounding, it is possible to create a safe and reliable electrical environment. In addition to the NEC requirements, there may be other applicable standards or regulations that govern the grounding of raised flooring. For example, some industries have specific standards for grounding in sensitive electronic environments. It's important to be aware of these standards and to comply with them as well. When designing and installing a grounding system for raised flooring, it's always best to consult with a qualified electrical engineer. An electrical engineer can help to ensure that the grounding system meets all applicable requirements and that it is properly designed and installed. Here are some additional points to consider when grounding raised flooring pedestals. Firstly, use listed and labeled grounding components. Listed and labeled components have been tested and certified by a recognized testing laboratory. This helps to ensure that they meet applicable safety standards. Secondly, properly torque all grounding connections. Proper torque ensures a secure and electrically conductive connection. Thirdly, protect grounding conductors from physical damage. Grounding conductors should be protected from damage caused by impacts, abrasion, or corrosion. Fourthly, document the grounding system. Accurate documentation of the grounding system is essential for future maintenance and troubleshooting. Fifthly, provide training to personnel. Personnel who work on or around the raised flooring should be trained on the importance of grounding and on proper grounding practices. By following these additional points, you can further enhance the safety and reliability of the grounding system for raised flooring.